All right, good afternoon again, everyone. I'm Alan Pincus. I'm the business manager for 3D printing and scanning technologies for Design Point Solutions, based right here in Clark, New Jersey. And today we're going to discuss metal printing, 3D metal printers, manufactured by, in particular, 3D Systems. We are a authorized reseller of all of 3D Systems 3D printing technology. And I just do want to caution that this is a high-level primer. We could talk about metal printing for hours, if not days or weeks. It's probably one of the more complex 3D printer technologies out there. And during a short little 30 to 40-minute discussion, it would be really difficult to get to all the key elements. So I hope you'll bear with me. If you're looking for deeper information, please don't hesitate to reach out to me after the webinar, and we can surely have more in-depth dialogues. So with that being said, let's just move on right to the agenda. It's relatively short. I'm going to do a 3D metal printing overview for those unfamiliar with the technology, just to give people an opportunity to learn more about how the printing technology works. We'll talk a little bit about the different types of materials that can be processed through the metal printer. We'll touch briefly on the various applications that we've come across at 3D Systems and Design Point when it comes to what are people doing with metal printing. We'll do very briefly, we'll touch on people very often asked, well, how strong are the metals after they've been sintered together versus whether they've been cast or machined. We'll touch briefly on that. Then I'll go through a slide showing the various 3D Systems metal printers. And again, this is all very high level. Be happy to have more in-depth dialogues with anyone who really needs to take it to the next step. And then we'll have a little short Q&A period. Hopefully more questions aren't created than the answers that I've provided in the presentation, although I actually expect that it's, again, this is a very in-depth part of the 3D additive manufacturing world. So let me just start with this basic understanding and overview of metal printing. It's actually very similar to the operation of 3D plastic printing, especially the powder-based printers. So for example, 3D Systems has what they call their Color Jet series, or X60 series, formerly known as a Z Corporation printers, and it uses a powder, technology and a binder to glue everything together. In the case of metal printing, it's a similar notion, but instead of a gypsum composite, it's metals or ceramics, and instead of a adhesive binder, it's a laser that's sintering the parts together. The powdered material is uniformly spread across the build platform inside the printer, and then the powder is leveled and compacted by a moving roller, which we'll talk about a little bit more because that's an interesting part of an advantage of the 3D printers, 3D Systems metal printers. And we've briefly touched on it. A laser will energize the powder particles and sinter or fuse the metal particles together in the desired pattern. And then another layer of powder is spread across the previous layer. The laser, again, it's spread and then compacted, and then the laser sinters the new layer to the previous layer, fusing all the particles together, and that process is repeated over and over and over thousands of times in a build, depending obviously on the geometry of the part or parts you're trying to make. And when it's complete, the part is removed and post-processed. The unsintered powder is recovered and reused. That's a key advantage, is that you have very little waste. If an object consumes by itself 10 cubic inches of raw materials, and in a subtractive environment you would cut away 20 cubic inches to get to it, generally that's wasted or has to go through a long recycling process. Here the powder is literally recovered and you can reuse it, and there's very, very little waste in a 3D printer. For precious metals, that's extremely important. So I've got, picture says 1,000 words. That means a video must be 10,000 words or 100,000 words. So I've got a couple videos here, short videos if you'll indulge me, show you a printer in operation. So right here you can see where it says the powder layering. I'm going to start this little video, maybe do a little, I apologize, let me back up, it didn't start. Sorry about that. So here we have the roller arm went across and back, and now you can see the high power laser is now jumping around the powder surface, and you're actually seeing the laser energy sintering together, melting together, or fusing, however you want to call it, the particles. I don't know what this powder is, but you can see it fusing together. I'll let this video finish. So as this completes, you can see that it's basically tracing out whatever this particular object is. I believe that this is some sort of a spinning turbine, and each of those arms that are shown there are the vanes of the turbine. In the next video, it's a little bit more informative here. We have a pattern of squares that are being created here. This is probably for test purposes, and when I start this video, you'll see the roller arm comes out. In the first pass, it lays down the powder, and in the second pass, it runs the compactor. So it compressed it together, and now the laser is going to come out and sinter the new layer to the previous layer, and it will repeat this process a number of times. So the roller comes out, spreads the layer. You can see it hides the previous work, compacts it, and now the laser comes and again sinters together the materials. Okay, and that's the end of that video. So essentially, this process is just repeated over and over. This is what we're showing are some relatively simple geometries here, but you can create almost infinitely complex geometries, and this is all done from obviously a design file that the printer software will slice up into microscopic layers, and each layer then is a 2D pattern that the laser sinters together, and then the layers are added together layer by layer by layer. Removing the parts when it's completely done is fairly straightforward as well. So this is an image of the same machine. There's two cavities there. On the left side is a hopper, and on the right side is the finished build. So when I start this video, what you'll see is the thousands of layers that were laid down is coming up out of the build tray, which drops, a thousandth of an inch at a time, and then the operator will reach in and he's simply brushing off the excess powder, metal powder. So imagine if this was silver or gold, just how important this particular step would be, where you're actually, looking at a huge amount of dust, gold dust or silver dust powder that you definitely want to reclaim, and it gets brushed into the opening where the hopper recovers the powder and it can be reused. So hopefully those videos gave some insight for those who are not familiar with the process, how the 3D metal printers operate. And again, it is very similar to the plastic printing idea of 3D printing, where it's a layer by layer recreation of the original object. When it comes to the metal printing materials, at least in the case of 3D systems, it's actually an open platform. 3D Systems doesn't believe in locking out this particular machine from using any powder supplied by anyone, for the simple reason that I don't think it's easy for them to envision where the future's going with metal and ceramic powder. So the good news is with the 3D Systems platform, I can't speak for other manufacturers, if you can get a metal powder that you want to try in this printer, you're more than welcome to try it. Obviously with guidance from 3D Systems, they'll be happy to help you try a new material. There are it is understood that most powders, if not all powders, can be sintered together. It's going to be a function of laser power and a bunch of other parameters that are pretty much well outside the scope of this particular webinar. But the most commonly sintered materials include steel and steel alloys, like stainless steel, 316L, 17.4, nickel alloys, cobalt chromium, aluminum alloys, titanium alloys, copper and copper alloys have been melted together, sintered together, tungsten, molybdenum, and as I mentioned, precious metals such as silver and gold have also been demonstrated that can be processed through the metal printers, as well as some ceramic materials have also been tested. Now, you don't necessarily have to ask me this question, how much do these materials cost? How vast is the ocean is probably the right answer for that, simply because aluminum, which is at the lower end of the spectrum, is probably $2 to $3 per cubic inch, depending on how much the base commodity is going for. And things like titanium are $40 to $50 per cubic inch, and gold is in the thousands per cubic inch. Definitely something, as you research this, you're going to want to learn about the pricing of these materials. 3D Systems and Design Point, we can help you gather that information as you do your analysis and research into these things. Applications are truly endless, but some of the places where we actually have an install base of 3D printers and they're actively using them on a daily basis for prototyping and as well as production. Here are a few of these places. The dental and orthopedic industries are huge with using the metal printers. They're printing bridges custom bridges for people's mouths. Anything where there's a metal post or metal required for use into dentistry or orthodontistry, 3D printing is right there with them. Orthopedic is also a huge place where 3D printers are used. We have at least one or two customers right in New Jersey that live and die by 3D printing technology. In fact, I can't say who the customer is, but the two images on the right come directly off of a metal 3D printer. The image in the middle are orthopedic bone screws and plates that are used to hold bones together, and the image on the right is a hip replacement, and those were made out of titanium metals and titanium alloys, and are probably right now in some machine somewhere in New Jersey actually being printed out right this very second to go in a particular individual's leg. They do also standard issue on the metal printers, but it's more likely that these are customized for a particular individual's need. Another area that's huge and continues to grow is the automotive industry. These are the two most common the most common place that the 3D printers for metal are being used is in tire treads. These are two images of two different types of the same tire tread, just from two different angles. This would be a very challenging, if not impossible, object to machine with a machinist trying to do this, create these tread patterns. So what's happening in the automotive industry is they're making better and better tires because they can make more and more intricate patterns to achieve the desired performance goals. It's opening up those markets for a company that is making tires. Now, someone out there may not be making tires, but you may be making rubber parts and need to make rubber molds. This may be a place where you can see a big advantage. More generally, we're seeing a lot of use in mold and die and precision parts. So on the left is a two-part mold, cavity mold for injection molded use. you can make the most complex, ornate type molds from these kinds of metal printers, things that you may not be able to make in the machining world. That's one of the key advantages. And on the right, these are some precision parts that were made that were prototypes that the customer wanted made so that they could evaluate what they would look like before in the actual material before they spent money on the castings or other spending a lot of money on machining. So that's one of the advantages of the metal printers, as I'm sure many of you can imagine. Prototyping becomes something that's more routine than, gee, we have to go spend thousands and thousands and thousands of dollars making molds to create one or two prototypes, or spend weeks in a machining process creating prototypes. The metal printers allow you to prototype, move into pre-production, and move into full production much more quickly. Another key area is aerospace, where parts are being made that would have been almost impossible to make on standard subtractive techniques. So, for example, you have turbine assemblies here that are shown that are on aircraft as we speak that are being made on metal printers. And there's hundreds of more examples, but I just picked a few fun ones to show what people are doing with 3D printers in the real world. GE, I'm sure everyone's heard of that company. These are jet engine fuel injectors for aircraft that they're making strictly on a 3D printer out of cobalt chromium. You're looking at an actual photo of one of the jet engine fuel injectors, and there was an article I read a few months ago that they're looking at spending, I don't know, $50 million or more over the next few years in 3D printer technology. Impellers is another area, especially with the government. We're talking to governmental agencies where they want to create impellers. They want to reverse engineer existing impellers off of ships that are no longer manufactured, and they want to reverse engineer them and print them out using 3D printers, because there's not really another easy way for them to replicate them, and the government believes that 3D printers is the way of the future for them and all of the parts that they want to replace or potentially create new complicated parts in the future that traditional manufacturing techniques make quite challenging. Jewelry, maybe it's obvious, but jewelry is definitely a space that this is growing. You can see those intricate jewelry models were made. I don't think those were made in particular out of gold or silver there. They were probably just replicas being made out of a less expensive material. But imagine making these using gold or silver right in a 3D printer. You'll get much finer quality than in casting or stamping. 3D printers, as they come down in price over the years, jewelry manufacturers are probably going to get more and more intricate with what the patterns they can create, and still be competitive, manufacturing as things move forward in the technology. There's also countless specialty parts and fittings. In this particular case, these were solid copper, made out of solid copper. So just want to show you that I believe the impeller was stainless steel. I think the jet engine fuel injector was cobalt chromium. The jewelry was also stainless. This is copper. And of course, pretty much the best part about 3D printing in my mind is that you can pretty much make other shiny things. So you want to make something shiny, we got a 3D printer, we'll make a nice pretty shiny thing for you. The key advantages of 3D metal printing, we've touched on some of them. I'd list them here. Just, again, be mindful that this is a primer level, top level document, and it would probably take us hours or days to go through really all the advantages and practical uses of 3D metal printers. But to me, to summarize, the key advantages are basically, first and foremost, it truly can reduce time to manufacture parts over traditional subtractive technologies, streamlining the operation, going directly from idea to part quickly and efficiently is really, I think, a key prime mover for 3D printing technology in the 3D metal space. It really does reduce waste of expensive raw materials. In the additive world, you consume what you actually need, and with very little waste, you can recover what isn't used. So again, as we saw in the video, the operator was brushing off the unused portion of the powder and recovered that. Is there loss? Yes, there is a small bit of loss. It's probably a practical impossibility to recover 100% of the material, but you're probably recovering a good 98, 99% of it if you're fastidious in how you recover it. Not such a big deal for maybe aluminum, which is far less expensive, but the precious metals, it's probably fairly apparent that you'd like to recover as much as possible. You can build prototypes, you can build production parts without long setup and lead times, and you don't need to go to other service providers, machinists, CNC machines, other castings and things for your prototypes initially, and then do your production parts. Here you actually could build a prototype, get it right, and it moves to being a production part. I think another key prime mover for the metal printing is you can create parts that would otherwise require multiple assemblies. So if you have a part screwed to another part, screwed to another part, and a part inside a part, and it's 5 or 6 or 8 or 10 different pieces all coming together, 3D printing is not limited by the physical need to cut parts separately and then bring them together. If you can envision it, you can design it in the 3D world, the virtual world, the 3D printer will print it. So it really streamlines assemblies, and even if the final item that your customer buys from you is more expensive than the sum of the parts, there can be a huge value add in the fact that they don't have to assemble it, I should have said it the other way around. Even if the finished part costs more to make, it can easily be recovered in the cost investment in labor, in assembly, in checking to make sure the part's assembled correctly, and failures in the field that occur from a misassembled part. If you need epoxies or other resins to hold things together, bolts, screws, things like that, fasteners, building one assembly with 3 to 5, 10 moving parts or separate parts in one assembly adds tremendous value, and 3D metal printing gets you there. One of the key issues that people talk about is accuracy, and in the case at least of 3D systems, their equipment's rivaling machine parts. It's better than cast parts for the most part, and it's rivaling machine parts. They're getting down to 20 micrometer accuracies in all 3 dimensions. So for those who don't think in metric, that's less than 1,000th of an inch accuracy. It's starting to really, people can really say, I would ordinarily machine this part, but 3D printing is getting to the point where you can trust what comes out of the printer as far as accuracy goes. And a common phrase that's starting to be used a lot more, and maybe you put in your own head, what's the key deal around all 3D printing technology? What's one of the key things? Complexity is free. We touched on it with the creating the parts with multiple that would otherwise be multiple assemblies. It doesn't matter how complex your part is anymore. In general, the 3D printers allow you to get around the limitations that are presented by subtractive technology, and pretty much anything you can think of, dream of, create in a 3D virtual world, and then send to the printer, it can recreate. Designing for manufacturability becomes a much, much faster process. As I touched on briefly, there's a myth about the 3D printed metal properties, and the myth is that sintered metal parts are not as strong as their raw material counterparts, and that was true up until the last few years, and is probably still true for a number of our competitors out there. The truth, at least in 3D Systems' case, they have a patented roller technology that compacts the metal particles together tightly, allowing them to approach 99% or better of the raw material densities. So on the image on the left, it's hard to tell, but that's what you saw moving back and forth on the video. It's got an assembly that comes out, and the first pass, as I said, it lays the layer of powder down, and the second pass is this compaction roller, which is densifying the layers together. I liken it to those that may be familiar with landscaping or building retaining walls, the soil compaction that you're supposed to use a vibrating compactor and do it in what they call lifts. So every 6 inches you tamp it down, tamp it down, tamp it down, the goal being to get the particles as close together as possible, the dirt particles. Here, it's the same notion. We're trying to get, there's air in between all the particles, and you're trying to well, in the case of the printer, it's actually not air, it's argon or other inert gases, but you're trying to squeeze them together to get rid of the spaces and then do the final fusing. So they are approaching, they have data showing they're approaching 99% of the raw material densities. And again, continuing on material properties, again, this is a very high-level primer type presentation, so forgive me if you wish you had more had deeper data here, but if you compare the sintered tensile strength in a 3D printer to the casting tensile strength, they show in each of these 4 cases, these were the 4 top most used alloys: stainless steel, cobalt chromium, and titanium alloy. These are the most common that seem to be used in the industry. In each case, the tensile strength of the sintered material was greater, significantly greater, than if you cast with the same materials. They do have some similar results on the original material being like in bar form, but unfortunately I didn't have all of the data consistent to show here, so I just wanted to summarize this. The data comes right from 3D Systems, and if you are interested in a deeper dive into this information, just let me know, and we can pull out some of the white papers, and I can forward them to you, that whatever information they've gathered on the studies. But I'm trying to dispel that myth that the material's not as strong as its casting counterparts or et cetera, to give you an idea as, hey, this is real. This is, we can make some really high quality stuff with a 3D printing technology. There are some things to think about. This is actually short. I mean, the reality is there's probably hundreds of things to think about, but I was thinking about this relative to the 3D printer world when it comes to the plastics machines, the plastics machines in general. You can plug them in an office outlet. It can run in your office. It it doesn't really emit much noise, much odor. There's not much dust. The plastic printers are definitely become much friendlier from an office environment. That's not so much the case with the 3D the metal printers. For example, you must consider your facilities when looking at buying a 3D printer that's the metal series. If somebody wanted to buy a metal machine today, you wouldn't want to do that until you understood the implications in your facility. For example, power requirements. None of these machines, maybe it's apparent to some people, but none of these machines plug into the wall. You need to bring in an electrician. You need to have no less than 240 3-phase. I think the smallest machine is 240 3-phase, up to 480, 460 or 480 3-phase, depending on the size of the machine. So these have some powerful lasers in them that need a fair amount of power to operate. Ventilation. You do need to ventilate this equipment to the outside environment. And there's an inert gas purge, so every time you seal up the build chamber when you're ready to start the new build, the first thing it does is it pulls vacuum and injects an inert gas. I believe it's usually argon in this case, because you don't want to have any oxygen left in the chamber. The laser will interact with the oxygen, and then you wind up oxidizing your metals. So you have to either be able to provide inert gas or just be aware of the fact that if you don't already have it, that you're going to need to add that. When it comes to material processing, the size of the build platform, I'm going to get to another slide showing the 3 different versions that are offered by 3D Systems. That's going to be a critical thing for you, because really the price of the system depends on 2 key factors. One of them is the size of the build platform and the power of the laser. So for example, in our smaller system, it's only a 50-watt laser, and I say only because it actually cannot sinter aluminum. as an example, aluminum has a high threshold of energy required to sinter the aluminum particles together. You would have to step up to our middle-sized one, which has a 300-watt laser. And so what types of materials you're processing definitely become a driver. So when you're investigating 3D printer technology, you're really going to want to understand, 80 to 90% of what you might process. Can it be processed in the printer you're looking at, and how big are the objects that you want to create? And when it comes to post-processing, nothing comes out of the machine finished. Structurally, yes. When it comes out, it's as strong as it's going to be, but you might have some secondary processes that you need to do. For example, the printer knows to create these small scaffolding supports in places where you have severe overhangs. For example, let's say you're creating an impeller and you have a severe overhang. Well, during the sintering process, the materials literally being melted, and when you melt a metal, it becomes very malleable, flexible. The machine will actually create some supports as for temporary use, which you then snip off, and then you may need to deburr. Just like other processes in machining, there's very little difference here. Is very little comes off of a CNC machine that doesn't necessarily need another final post-processing of some sort of polishing, of buffing, things like that. So you will have the similar things that you need to do here. Another thing that happens here that may not happen in other machining environments is you actually have to separate your part from the build tray. When you're building in stainless steel, for example, the build tray itself is stainless steel. You may get several hundred uses out of that stainless steel build tray, but between each use, for example, when you cut away or remove using cutters or using EDM, when you separate your part from the build tray, you would then need to just quickly grind or polish your build tray, and over time you're going to grind away the build tray and over time need to replace it. So it's a sacrificial build tray, but you're probably going to get hundreds of uses out of it because kind of like a brake rotor, you need to turn the brake rotor every so often, and you can do that a number of times. That's the same exact concept here. When you want to build instead of I can't remember the example I gave. If it's titanium instead of stainless, you actually put in a titanium build tray because you want to be able to bond to the build tray using titanium to titanium. So there are those kinds of things you have to be aware of when it comes from separation of the build tray as well, and the finishing requirements. As I mentioned, you might need to deburr them, you might need to brush, you may need to put them in a sandblaster. You may need to plate it. It all depends on your final use of the part. But again, coming out of the printer, it's ready for those things. There's you don't have to strengthen the part after the fact. In other words, you may. Again, I am not a metals expert or a machinist, so forgive me if I'm not speaking correctly to those out there that are in the machinist metal world. In fact, send me notes if I've said something incorrectly. I always like to learn, so I appreciate that. Briefly talking about 3D Systems metal printers, there are only 3 flavors right now. They have their ProX 100. And again, as I mentioned, the 2 key drivers are the build size and the laser power. So this one has a build envelope of 4 inches by 4 inches by a little over 3 inches and has a laser power of 50 watts. And this will sinter together the majority of the metals, exclusive of aluminum and a few others, because those requiring significantly more laser power. The laser power also affects speed, so if you have more laser energy, you can move around faster. So there are trade-offs with the laser power as well. This machine starts at retail price around $300 to $350, depending on configuration. That has nothing to do with the facility's requirements or other things related to the machine that you may have to sort out before purchasing it, but that's a rough number to just get the capital equipment that you need to start moving in the right direction. The next step up is the ProX 200, obviously a bigger build size, almost 6 by 6 by 4, much more powerful laser, 300 watts, and again, price bumps. You're now at the $500,000 point, about $500,000 to $600,000, because there are some configurations and things that accessories you may buy to work with the machine. And the big daddy is the ProX 300. The build size is 10 by 10 by 12. Laser power is 500 watts, and this one's pushing, the high end of the, six figures between, $800,000, $900,000. So that really runs, the gamut, 300,000 to about 900,000 when it comes to 3D systems, direct metal printers, and then obviously facilities and material costs and things like that would have to come into play. So hopefully I've shared with you their product offering well enough. And essentially we're at, I can't believe it, timing's perfect. We're at the Q&A session. I really appreciate your time. A couple things to bring to your attention. Shortly when this webinar ends, we are going to email you a survey. And if you'd be so kind as to fill out the survey, it's only a few questions so that we can learn more about how we can assist you in your 3D printing research. Really would appreciate that. It'd be a big help if you don't mind. Love to learn more about what everyone's doing out there and why you're interested in 3D printer technology. Also want to mention that there's some promotions right now on 3D printer equipment. If you need a scanner, for example, I don't know who's out there looking for 3D printer scanners, 3D scanners. We have some bundled programs. If you're looking for a printer and you also need scanning capability for reverse engineering or inspection, we have some promotions right now. And we have a trade-up program also. Do you have an old machine? If there's anyone out there with a 3D printer and you're trying to get rid of it, and that's one of the reasons you haven't maybe upgraded to the latest technology, think about that. Let us know that you have an old FDM machine or an old Objet or an old ProJet and you're interested in upgrading it. Give us a call. And then lastly, I just want to mention we've got a training class that we'll be sending out information on. In the early fall, we're having a training class where you can learn about the major 3D printing technologies, how 3D printing works from beginning to end, including basic design for 3D printing, verification of your models so that you get a good print, optimizing for time or cost, and post-processing. The program's meant for the novice, to maybe people that are interested and don't have that much experience in the 3D printing world. And we also have special pricing for students. So if there's any students out there listening and you'd love to be certified as a user or someone knowledgeable in the 3D world for future employment opportunities, please let us know, and we have special pricing. And don't hesitate to send me an email. You can see my information's right there, apincus@design-point.com. And I'd like to open it up for a couple minutes to questions. So if you type in your question, if you're interested, if you like, let's take a moment and answer some questions. So I'll wait for some questions to come in. And in the meantime, some upcoming events while I'm waiting for some questions to pop in. We have Design Point Solutions not only sells 3D systems printers. Design Point's a world-class sales and support organization for SolidWorks and has been selling and supporting SolidWorks customers for over 15 years. And they have a lot of webinars and hands-on test drives you can check out. And every month we try to have we have been having a monthly printing technology, something like this webinar that you've attended. I'd love to have you join another couple if you'd like over the coming months. We'll be talking in general about scanning, the plastics printers, mixed material printers, stereolithography printers, selective laser sintering machines, and our ColorJet technology as well. You can find out more about what events are coming up if you just go to our website, www.design-point.com/events. Poke around our website. You'll see what's going on there. And let me take a look, see if there's some questions. There aren't any questions yet. Let me see here. Let's see here. Why isn't it opening? Bear with me one second. I apologize. I'm having trouble having it. I see somebody's submitted a question, but I don't, for some reason, can't see it. This is embarrassing. I can't see the questions. I really apologize. I don't know why. So I apologize. I'm not sure what's wrong. I just see a couple questions, not too many. I'm unable, the interface is for some reason not working properly, and I cannot actually read the questions. So what I'd like to do is just thank you for your attendance. I had a lot of folks out there join. Please do me a favor, if you had a question and you were trying to have me answer it, please just send it to my email. I'll be happy to personally respond to it as soon as I see it and have an answer. I'll get right back to you. Again, my email is apincus, APINCUS, at design-point.com. And again, thanks for joining, and I look forward to seeing you soon or talking to you soon and maybe then a future webinar. Take care, everybody. Thanks.